Welcome to AP Chemistry. In this video, we're going to be going over Unit 1.4, Composition of Mixtures. And our essential knowledge here is says that pure substances contain atoms, molecules, or formula units of a single type. We talked about pure substances in 1.3, and now we're talking about mixtures. And so it's differentiating right here on this essential knowledge of between pure substances and mixtures. Pure substances are of a single type, while mixtures contain atoms, molecules, or formula units of two or more types whose relative proportions can vary. And so we looked at the law of definite proportions for pure substances. For mixtures, it is not necessary, or it is not true, that every mixture is going to contain the same proportion of each type of molecule, formula unit, or atom. And so that's what we're going to see in this lesson. So we start the overview with pure substances. We know pure substances form matter that have definite and uniform chemical composition. They have distinct properties. They cannot be separated, and their properties remain constant under various conditions. There are two types of pure substances: elements, the simplest form of matter that cannot be broken down by simpler means, substances by chemical means. They consist of only one type of atom, oxygen, gold, and here it's oxygen, it's molecular oxygen, but it's still considered under element. Gold, anything that you find on the periodic table. Whereas compounds, those are substances made up of two or more elements, and I think we're all familiar with those, like water, sodium chloride, and the such. Today, our focus is, again, we see the difference to differentiate between pure substances and mixtures. We talked a lot about pure substances in 1.3, so we're going to focus more on the mixture aspect of this essential knowledge. So mixtures are combinations of two or more pure substances that are physically combined. They are not chemically bonded together, and they can be separated. So we have two types of mixtures: the homogeneous and the heterogeneous mixtures. Homogeneous mixtures have a uniform composition. The components are evenly distributed at the molecular level. So we cannot distinguish between one substance and another in a homogeneous mixture. But a heterogeneous mixture, mixtures that do not have a uniform composition, we can clearly distinguish between the components of that mixture. For instance, if we have a mixture of sand and water, we can see that. We can see components of solid. We could see gravel, different types of rocks, sand, pebbles, all those type of things. All right, and so that's just kind of going over that essential knowledge. There's not a whole lot here. However, we are going to look at mixtures, and some of this we're going to be doing in the lab, so we need to make sure we understand some of this conceptually, and that we can math our way through some of the problems that we're going to be receiving. So on this question number 1, I started off with a particulate model, and I like to use particulate models because AP likes to use particulate models, and it's just so easy to interpret them. But if we don't work on them in class, then when we get them on a test and we see them, they can be kind of confusing, when in reality they're so very easy. So in this sample here, we see that we have this molecule here made up of carbon with 2 oxygens, and then we have another type of molecule with a carbon and 1 oxygen. And because all of these molecules are not the same, we have one carbon dioxide, we have carbon monoxide. Because they're not all the same, we know that we have a mixture, and we're going to assume these are gases here, especially by the way they're in that container. But so we have a mixture. Of carbon dioxide and carbon monoxide. So in this sample, a pure substance or mixture, well, it's going to be a mixture. All right, and so we're going to say mixture. Why? Because it's made up of more than one type of substance. All right, it's made up of carbon dioxide and carbon monoxide. In all likelihood, this is in the air. It's a gas. It's going to be a homogeneous mixture. We wouldn't be able to distinguish between those parts. But we're looking at a particulate model. It's really hard to tell from a particulate model standpoint whether that's going to be homogeneous or heterogeneous, but I would say that it's going to be homogeneous. So all we are asked to do is say, is it a pure substance or a mixture? And it clearly is a mixture. And then it says, what is the percentage of oxygen by mass in this sample? So again, this is just like another mass percent problem. all you have to do is look at the total mass of all the particles in the system, and then you take the component of that you're looking for, like oxygen, you divide it by the total mass and multiply by 100. And so how do we do that? Well, we first start by looking at the components. And since we're asked about oxygen first, we'll start with oxygen, and we'll say that we have in our picture, and according to our key, we have 1, 2, 3, 4, 5, 6 oxygen. So we're going to first of all define this, and we're going to say, we're gonna find the mass of oxygen. Mass of oxygen. That's what we need to find. And so we define this, and we say, there we go. This is going to be equal to the number of oxygen, and the number of oxygen. Let's just go ahead and put this in. It's going to be 6, and then we're going to multiply that by the molar mass of oxygen, because that's the mass that we have available to us. And so we're going to say it's 6 times 16, and that's where we get that from the periodic table. And so our total mass of oxygen is going to be 96 grams. All right, of oxygen. So there's our mass of oxygen. All right, and we would be able to figure out the mass, the percentage of oxygen by mass, if we knew the total mass of all the components of this mixture, but we don't. We are missing the carbon. So let's go ahead and look at the mass of carbon. So the mass of carbon is equal to the number of carbon particles, which is 1, 2, 3, 4. So we're going to put 4 times, and we're using our periodic table from AP, it's 12.01 grams. And so what we end up with is 48.04 grams of carbon. Now, if we want to get the total mass, we just have to take the mass of carbon plus the mass of oxygen, and that's going to give us our total mass. And so I'm not going to come up with a formula for that. We're just going to show us adding that, and I think that will work just fine. Well, actually, let's just come up with a formula for it. So let's say total mass is equal to mass of oxygen plus mass of carbon. And so this is equal to, and we can see this very easily, we can see that this is 96 grams plus 48.04 grams, which is equal to 144.04 grams. All right, so 144.04 grams. So that's our total mass. So now that we have all of that, all we have to do, see if we can get that in there. There we go. Total mass is 144. So now all we have to do is take our percentage of oxygen. So if we want to find the percentage of oxygen, we're going to percent mass of oxygen. We're going to take the mass of oxygen. I'm just going to put mass O over total mass. And then we're going to multiply by 100%. And that's all we do. So we simply take those values that we already know. And if you can't see what you're looking at, you just move this guy and you can see what you want to see. And we see that we have 96 grams of oxygen, and the total mass was 144.04 grams. Then we're going to multiply by 100%. And when we do that, we're going to end up with 33.35%. So let's just say 33.3%, and let's go ahead and call that oxygen. So our answer is 33.3% oxygen. Make sure that's correct. Yeah, that's correct. No, that's not correct. I got the wrong value in here. It should be 90. I thought that was a little bit low. I put the wrong, that's for the carbon. All right, 66.64% or 66.65%. So we're just going to say 66.7. Let's go ahead and say 66.7. Sorry, I put in the wrong value there. Looking at the wrong thing on my calculator. So it's 66.7%. All right, it's close enough. that we'll call it that. All right, so sorry about the mistake there. So 66.7% oxygen. All right, if you watch the video and skip and just pick up stuff, you're going to probably get the wrong answer there. But that happens. I made a mistake looking at my calculator. So now we're going to look at the percent mass of carbon. And we're going to see that this is equal to the mass of carbon. We'll just put mass C over total mass. And again, I'm just defining these things so that we know what I'm doing. I could most certainly just go ahead and plug these in for us, and without a doubt, I'd do this much faster if I did not define everything. But maybe it's a little bit easier for you if I do. So here, the mass of carbon, now I have this right, it's 48.04 grams over 144.04 grams. And then that's going to be multiplied by 100. And what we end up with there is, now it's going to be 33.3%. All right, and what we notice when we do this is that these two values actually both add up to be 100, because this entire mixture is made up of only carbon and oxygen. So the percentages must sum to 100%. And so we can say that this one is 33.3%. All right, and so that takes us to our answer. Just to make sure that we our grader knows what our answers are, we go ahead and put a rectangle around it, and they look good. All right, so we can move on to the next one. This next one we look at and we see we have to just differentiate between element, compound, homogeneous mixture, heterogeneous mixture. And so we have glucose. Glucose is a compound, obviously. We see the chemical formula for it. It's a molecular compound in particular, but we just need to put compound, and we get credit for that. We got a bowl of cereal with milk. This is going to be a mixture. Can we distinguish between cereal and milk? Yes, so we're going to say heterogeneous mixture. Then we have brass, an alloy of copper and zinc. Okay, this again is a mixture. And this is going to be, we're not going to be able to see the difference. We're not going to be able to distinguish between copper and zinc in the brass. So we're going to say this is a homogeneous mixture. All right, and then graphite, which is a form of carbon. We find carbon on the periodic table. That means if we find it on the periodic table, that is an element. Sugary water. Sugary water is sugar dissolved in water. And sugar dissolved in water creates a uniform look. We cannot distinguish what is sugar, what is water, and so we would call that a homogeneous mixture. And then water and oil. You know that water and oil do not mix. They would form separate layers. And so this would be a mixture, even though they don't mix, but it would be a mixture, but they would separate into separate, very distinguishable layers, and so we call it heterogeneous mixture. All right, and that's as easy as question number 2 is. Let's go to question number 3, and I talked a little bit about this in class. This is a very important concept right here, especially in 1.4. I see this assessed in many ways. Here I assessed it in the form of a word problem. It could be in the form of a particulate model. It may have different particular models that show various compounds of carbon dioxide and carbon monoxide, or various compounds, and they want to know which of these has the highest percentage of carbon or oxygen or even hydrogen, if we had some hydrogen in the mix. So you might have to look at this type of problem through many different lenses. Here we're going to just look at it through this word problem lens. And so we see that we have this sample of sodium chloride, which is analyzed and found to contain 75% chlorine by mass. Pure sodium chloride is known to be 61% chlorine by mass. Two scientists, Dr. Sharma and Dr. Ben Carter, are debating the composition of the impure sample. So we know it's an impure sample because, according to the law of constant composition, or the law, let me go back. Yeah, according to the law of constant composition, we see that any sample of sodium chloride would need to have a 61% chlorine by mass composition. So, or the law of definite proportions, interchangeable terms. So we see because this sample has something different than a 61% chlorine by mass composition, that it cannot be pure sodium chloride. It has to be mixed with something else. So Dr. Sharma says sample is mixed with potassium chloride. Potassium chloride is common. We can see that, and it's found easily. And so most likely it's going to be the potassium chloride, and potassium chloride actually has a larger atomic mass than sodium, keeping the chlorine mass percent in each compound high. Now, the problem with that is that if we look at potassium chloride, KCl, let's go this route here. Let's go to add math. And we look at, if I can get that in there, yeah. So we look at that, we can see that if we look at the percent of chlorine, let's do this, percent of chlorine in KCl, so we're going to put KCl here, is equal to the mass of chlorine divided by the mass of KCl times 100%. All right, so we're going to see this times 100%. And so we're trying to look at Dr. Sharma's proposal here. So if we look at, and I'm going to have to get a periodic table real quick. Whoops, there we go. If you haven't discovered ptable.com yet, you should probably do that. And so we can see, get my calculator out too. So we can see the mass of chlorine is 35.45 grams. And then the mass of potassium chloride would be 35.45 plus the mass of potassium, which is 39 let's say 10. And so we end up with, well, I didn't put it in that way. All right, so let me get that squared away. Okay, I'll get that number to you. All right, and that is 74.55. All right, so we end up with a mass of chlorine, which is 35.45 grams. The mass of potassium chloride, which is 74.55 grams. And so we multiply that times 100, and we end up with 47.55%. All right, so 47.55%. So if we mix, and let's say this is, let's just go ahead and say that this is less than 61%. All right, so if we mix sodium chloride with potassium chloride, I want you to see Dr. Sharma's argument. Dr. Sharma is saying that potassium has a larger atomic mass. It does. So potassium has a larger atomic mass than sodium. Potassium's molar mass is 39.1, whereas sodium's is 22.99, or basically 23. So potassium actually has a pretty high molar mass. And if we compare, how do we get the percentage of sodium chloride? Let's go ahead and look at that. So if we get the percentage of chlorine in NaCl, we look at this, we're going to see, once again, that we have 35.45 grams. So our numerator is going to be the same. But because our bottom number is smaller, so it's going to be 58.44 grams. And this is due to sodium having a smaller molar mass. As a matter of fact, let's do this. We said this was 23.00. We're going to just say 23 for sodium, plus 35.45. And then we said this is equal to, and we'll plug in these values, 35.45 grams. I'm going to put grams here. And this comes out to be 58.44 grams. All right. Times 100. And so this says this is 61%. All right. And so there we are. So that is 61%. So let's do the same thing here just to make it abundantly clear. So maybe I didn't put in something right here that I should have. I should have said mass of Cl over mass of NaCl. All right, then we'll go equals. All right, that may be a little more clear now. And then maybe one thing that I could do here is I could say this is equal to, I'm leaving a lot out actually. Let's go do this, times 100%. There we go. Now that's actually perfect. So here we could do the same thing just to make sure that it's a little bit easier to read. We can say here that we have 35.45 grams. And let's break this up into 35.45 grams plus, and then we'll put in, let's actually do this other way. Let's do this the same way, same formatting. Let's say 39.10 gram plus 35.45 grams. All right. And then we can put in times 100. Maybe this Greek letter thing is getting to me. Times 100. There we go. All right. There we go. Got it now. All right. And then this is equal. All right. So now we have it all there. All right. So what we're seeing here, and this is what Dr. Sharma is saying, I just wanted to make it abundantly clear. Dr. Sharma is saying that both are common salts, and adding KCl would increase the overall chlorine percentage since potassium has a larger atomic mass than sodium. Now notice, what does the larger atomic mass of potassium actually doing? It's actually increasing the mass of the denominator, all right, by which we calculate this percent mass. And when that happens, we take the numerator is still staying the same. So what it's doing is it's actually, because this value, because the mass of potassium is higher than the mass of sodium, it's actually decreasing the overall percentage. And so it's making it less than 61%. So Dr. Sharma's argument saying that the larger atomic mass of potassium is causing the mass percent to become higher is invalid, because it's actually making it lower. All right. And so that's why we are going to disagree with Dr. Sharma. But I wanted to make sure we clearly understood the argument. So Dr. Carter says that's not right. The sample is clearly a mixture of NaCl and lithium chloride. Now, I don't know that it's clear, but if we were just given two choices between potassium chloride and lithium chloride, well, then it would be clear that it is lithium chloride. So the overall chlorine mass percent is significantly higher than pure sodium chloride, and adding a compound with a lighter cation like lithium would be the only way to substantially increase the mass percentage of chlorine in the mixture. So if we look at the percentage of, let's look at this, of chlorine in lithium chloride, we can look at Dr. Carter's argument. So we can say the percent chlorine, and this time let's say in lithium chloride, and we'll follow the same format this time, maybe not botch it too much, as the mass of chlorine over the mass of LiCl. And that's going to be times 100%. Let me get that out of the way. 100%. And then this is going to be equal, all right, to 35.45 grams. And I want you to notice this. We see that this number, or the mass of potassium, was larger than the mass of sodium. And look at the mass of lithium chloride. It's 6.94 grams plus 35.45 grams. All right, so we plug that into our calculator and we get 42.39. And so we better make sure we put in this times 100%. All right, and this is equal to 35.45 grams over 42.39 grams times 100. All right, so we notice that our denominator is actually smaller, and 35.45% becomes a larger percentage when the denominator is smaller, right? And it's smaller because the mass of lithium is less. And so all we have to do is we put in 35.45 divided by 42.39, and we get 83.6%. All right, and I'm going to say 83.63%. 83.63%, which is what? Greater than 61%. And it stands to reason that if we're going to get a compound that is going to increase the percent of chlorine by mass in the mixture, we'd have to have a compound that has greater than 61% chlorine. And because lithium has a smaller mass than sodium and potassium, it must be the lithium. All right, in this case, it definitely wouldn't be sodium because we know it's a mixture. So if we're just comparing between sodium and lithium, it would have to be lithium in that case. All right, and so that's the argument that's being made here in this one. And if we look at our choices, some of the things I already shared with you, what we would see when we answer our question is we want to make sure that we, first of all, answer the question, Dr. Carter is correct. Which scientist is correct? Dr. Carter. All right, and we want to say because the mass percent of chlorine is higher in the mixture with lithium chloride. And that's what we see here. The mass percent of chlorine in lithium chloride is higher than in the pure sample, which is this, higher than 61% because the mass of the cation is small. Because the mass of lithium, the cation, is small, the percentage of chlorine in the sample is large. And we see the mass is small, the percentage is larger than 61%. All right. So that's what we're getting at. So while mixing potassium chloride does increase the total amount of chlorine, yeah, if we put potassium chloride with sodium chloride, it's going to increase the amount of chlorine versus not putting the potassium chlorine in there, but it's actually going to lower the percentage that we have in the mixture. And I'm not showing you my calculations there, but if we looked at assuming, and I'm not giving you my exact answer here, but whoops, that ain't it. Control Z, let's do this. All right, there we go. And let's put this in there. All right, so if we see this, we see that if we assume that we have equal amounts of the potassium chloride and the sodium chloride, we would end up with actually a lower percentage than 61%. That's what this is saying. And that just is good reasoning. All right, if we look at lithium chloride, the mixture with lithium chloride, we know that it increases the mass percent, and I may have already stated this just be overstating it, but the mixture with lithium chloride increases the mass percent in the mixture because its mass percent of chlorine is higher. So assuming the mixture contains equal masses, we'll show a very similar calculation. We assume that they have equal masses. We don't know what that mixture is, so we're just saying, what if it's a 50-50 mixture? Does it cause an increase in the overall percentage. And what we see is, indeed, it does. It goes up to 72.32%, which is much greater than 61. Now, we notice that the original sample was 75%. What does that mean? Just means that we don't have a 50-50 mixture of the lithium chloride with sodium chloride. We don't know what that mixture is. We're not tasked with figuring that out. We most certainly could, but that's not the overall arching theme here. It's just to understand the cause and effect, or the relationship between the mass of the cation and the overall percentage, and how that affects the percent of another ion. And so, again, you might be looking at a problem that deals with a written scenario. You might be looking at a very straightforward problem that asks you which is going to have the highest chlorine content, sodium chloride, potassium chloride, or lithium chloride. And if you see a scenario like that, well, you know they all have chloride as the anion. The one that's going to have the highest percentage of chloride is going to be the compound that has the cation with the lowest molar mass. And so it's just some things to look at. Look at those type of relationships, and you'll be okay on any problem that I'm giving you. All right, moving on to the next thing. We see in this next one, here we go. We have a 5-gram sample of an impure iron ore known to contain iron 3 oxide as its only iron-containing compound, and it is analyzed. It is found to contain 3 grams of elemental iron. Given the theoretical percentage of iron in pure iron 3 oxide is 69.94%. Calculate the percent purity of this iron 3 oxide in the original 5-gram sample. All right, so that's what we're end up doing, is calculating the purity, but I put part A in here to kind of help guide us. So it says calculate the actual percentage of iron in the pure sample, or in the impure sample, excuse me. So in the impure sample, we know that we want to calculate the percentage. So we're going to say the percentage, and we know this is by mass. And let's go ahead and state that this is impure. And if I could see, that would be nice. Percentage of impure is going to be equal to the mass of this, the mass of iron. Let's say mass Fe, and this, of course, is of the impure sample, over the total mass. And what we can say, and I say total mass of the impure Fe2O3 sample. But then we're going to multiply that by 100%. And again, we plug this stuff in, and we get 3.00 grams of Fe over 5 grams. And let's say a mixture. I'm just going to put mixture because we don't know what it is, or we can say Fe2O3, and then we can just simply put in over here impure. All right, and then we multiply that by 100, and we end up with something like 60%. All right, so 60% Fe. All right, Fe. So 60% iron. Now, what does that tell you? That tells you that this sample of iron 3 oxide is most certainly not pure. Because if it was pure, it would follow the law of definite proportions. We would see that it had exactly 69.94% iron in it. In fact, it has less. All right, and so we want to know, what is the percent purity? Well, there's a couple ways of doing that. One way is really easy. If we want to know percent purity, we could say what we should have. We can say that we have is equal to what we have is percentage of iron Fe in impure over percentage of Fe in pure times 100. All right, and so all we have to do is plug in some values here. Plug in these values. The percentage here would be 60%. We just calculated that. So 60% over 69.94% that was given. And then we multiply by 100. All right. And with that, we end up with 85.79% pure. So this sample of iron 3 oxide is not pure. It is 85.79% pure. And that is probably the easiest calculation that we can do, if I'm being honest, because we're already given these values. Now, another thing we can do is we could apply the law of definite proportions in part B. So let me go ahead and make sure I put this in here real quick. Let's label this. This is part A, and this is also, this is part B. And so while I'm not super particular on your work that you do that, it is nice if you label your stuff for your teachers. I don't care what class you're in or what AP class you're in. If you're taking a test for them, if you label that stuff and you make it easy for them to grade, then it's easy for them to find your answers, and it's easy for them to give you credit. So if we look at part B, we can do another way of doing this. We can first assume that we have a pure sample, that a pure 5-gram sample. And if we do that, we can say we have 5.00 gram sample of Fe2O3. And if it is a pure sample, and again, we are just simply applying the same numerical values, and it's a pure sample out of 100 grams of Fe2O3, we would know that 69.94 grams is iron. And we would then know that 3.497 grams of that would be iron. So in a pure sample, and a pure 5-gram sample of iron 3 oxide, 3.497 grams is iron. So if we want to get the purity, we want to get the percent purity, what we're going to then do is take the mass of Fe, and let's say impure, that's in the impure sample, and then we're going to divide that by the mass of Fe, and let's say this is in the pure. So there's many ways to do this. So, and then we're going to multiply that times 100. And so what does that come out to be? This comes out to be the mass of iron in that was 3.00 grams. That's given. We found that this was 3.497. And then we multiply that times 100. And we end up with 85.79, 79%. All right, the same answer. All right, so it's the same answer, and it wasn't ever going to be a different answer because that's the purity of that substance. All right, so however you want to do it, I like the first method just because it is one step. We already had the information that we needed to do it. Here we had to kind of go determine the overall mass using the information we had, but either way you land in the same place. So that's question number 4. All right, let's go to question number 5, and then we're going to end this video. So on question number 5, we got a lot of things to going on here. It says a 15-gram sample of impure copper 2 oxide is analyzed. It is found to contain 11 grams of elemental copper. Given the theoretical percentage of copper and pure copper 2 oxide is 79.89% by mass. Calculate the mass of impurities present in the original 15-gram sample. Okay, so again, we're going to calculate the mass of the impurities. We're going to do some of these other calculations to help guide us to make sure that we have the information we need. All right, so we're going to go into show your work. It says calculate the actual percentage of copper in the impure sample. All right, so we have to calculate the actual percentage of copper in the impure sample. So we're going to start with percent copper, and let's go ahead and label this impure. And so we can say this is equal to the mass of copper. And I believe this gives it to us 15 gram sample is contained, is analyzed, it is found to contain 11 grams of elemental copper. All right, so we know this is going to be the mass of copper in that impure sample. And so this is of the impure sample divided by the mass of the sample. All right, and then we're going to multiply that by 100%. And so what does this come out to be? Comes out to be the mass of copper, we says 11.0 grams of copper. And the mass of the sample, and this is going to be 15.0 grams. And this is CuO, and then let's just make sure we know this is the impure sample, all right? And then this is going to be times 100%. And this is equal to 73.3% copper. All right, and so that's what we get as our answer. And of course, we got to make sure that we put our answers in the response box as well. That's as easy as coming over here, copying, Control-C, and then hitting Control-V. And there it goes. And hopefully you're getting credit. I don't know that I have this on feedback because this is a copy outside of our classroom. So calculate the percent purity of the copper oxide, copper 2 oxide in the sample. All right, so again, if we want to know the purity, we just did a sample we just did a problem like this a second ago, looking at the purity of the iron 3 oxide. And we said, well, if we know the percentage of both, well, then we can just use that to determine the percent purity. And so that's what we're going to do. We're going to go the faster method. So this is going to be the percent purity, and that's going to be equal to the percent of copper in the impure, and I can't spell impure real fast evidently, and over the percentage of copper in the pure. And we're going to multiply that by 100%. All right, and so now what we end up with is, we just said this was 73.3%, and the an actual pure sample, it is 79.89%. So 79.89%, and so we multiply that by 100, and what we end up with is 91.79% pure. All right, so the purity is it's 91.79% pure. So this copper oxide, pretty pure, but it's not completely, it's not 100% pure. Then what we look at is part C. It says calculate the mass of pure copper oxide in the sample. So we're going to calculate the mass of pure copper oxide in the sample. So how do we do that? Well, if we know that the pure sample is if we know that it's 91.79% pure, well then out of that copper oxide, out of the total mass of the copper oxide, we can figure out that out of 15 grams, 91.79% is pure. So that's all we have to do is use our answer in part B. So we go to C, and we say that we have 15 grams of CuO, and just to make sure we know this is an impure sample, but we know that in this impure sample, we know that CuO impure is, and we need to be a little more specific about that. We know that 100 grams of copper oxide, the impure copper oxide, is 91.79 grams of CuO. You see that? Because it's 91.7% pure. All right, and then what we're going to do here is we're going to distinguish this as saying it's pure. All right, and so now we know the mass, grams of CuO and we're going to make sure we distinguish this as pure. And what we end up with is 13.77 grams of pure copper oxide. So in that sample, in that 15-gram sample, 91.79% is pure. If we wanted to put that same value as a mass, it's 13.77 grams. All right, and then what is the mass of the impurity? The mass of the impurity in part D is going to be mass of impurity. This is actually a pretty easy calculation, is the total mass. That's going to be 15 grams minus the mass of pure. And let's just say CuO pure. And we just calculated that. And so this is going to be equal to 15.0 grams minus 13.77 grams. I guess it's 7.7 or 7.9. I don't know what I said. 7. I think it's supposed to be 7. Yeah, it's supposed to be 7.7. I think. I don't know if I typed something wrong. Y'all have calculators. Y'all figure it out. So 15.0 minus 13.77. And let's say it's 1.23 grams. Yeah, I think that's 13.77. 1.23 grams of impurity. All right. Let's say impurity. Yeah, 1.23 grams of impurities. There we go. I got it in there. All right. So that's what that looks like. And so you can plug all of those things into your handy dandy answer box. All we're looking for is the answers. We're not looking for all of the work. The work stays here. Things that you should put in the answer box: 73.3, 91.79, 13.7, and 1.23. And I don't know if I have it coded exactly that way, but most certainly I have it in there. Put in 1.23, 13.77 grams CuO, and then 91.79%. All right, and so that's all we have for questions 1 through 5. I hope that helped. For now, thank you for watching. Please like and subscribe.